Yes, the orientation of the conduit, whether horizontal or vertical, matters when derating wires in conduit. In vertical conduits, heat rising can cause a reduction in ampacity, specifically for continuous loads. However, the ampacity of wires in vertical conduits is not reduced for non-continuous loads, which are loads operating for less than 3 hours per day. In contrast, for horizontal conduits, the ampacity of wires is not reduced for either continuous or non-continuous loads. The National Electrical Code, or NEC, addresses these considerations in Article 310.15 Cone N2. Specifically, 310.15 Cone addresses vertical conduits. It states that for continuous loads in raceways, the allowable ampacity of each conductor shall be reduced as shown in Table 310.15 Cone unless the vertical raceway or enclosure has been approved for the conditions of use or unless proven by calculation that the conditions of use are within the ampacities given in Table 310.16. Note that for derating factors in other vertical raceways or enclosures, see Table 310.15 Cone. 310.15 C2 then addresses horizontal conduits. It states that for conductors installed in horizontal raceways or enclosures, and for conductors installed in vertical raceways or enclosures under the conditions described in 310.15 Cone, the allowable ampacity of each conductor shall be reduced as shown in Table 310.16 for the number of conductors installed and for the size and type of the raceway or enclosure. In summary, firstly, consider the orientation of the conduit, whether it's vertical or horizontal. Secondly, determine if the load is continuous, meaning it operates for 3 hours or more per day. Thirdly, for vertical conduits with continuous loads, apply the ampacity reduction factors found in NEC Table 310.15 Cone. Fourthly, for horizontal conduits, no ampacity reduction is required regardless of whether the load is continuous or non-continuous. Fifthly, always consult the latest edition of the NEC for the most accurate and up-to-date information and specific requirements for your installation. Understanding ampacity derating is crucial for ensuring the safety and longevity of electrical systems. Overheating conductors can lead to insulation breakdown, short circuits, and even fires. By following the guidelines in the NEC and considering factors such as conduit orientation and load type, electrical professionals can design and install systems that operate safely and efficiently. When dealing with multiple current-carrying conductors in a raceway, it's important to consider the cumulative heating effect. The more conductors that are present, the higher the ambient temperature within the raceway, and the greater the need to derate the ampacity of each conductor. The NEC provides tables and formulas for calculating the appropriate derating factors based on the number of conductors and the ambient temperature. In addition to the number of conductors, the type of insulation used in the conductors also affects their ampacity. Some insulation types are rated for higher temperatures than others, allowing them to carry more current without overheating. The NEC specifies the allowable ampacities for different insulation types based on their temperature ratings. Furthermore, the ambient temperature in the area where the conduit is installed can also impact the ampacity of the conductors. If the ambient temperature is higher than the temperature for which the conductors are rated, the ampacity must be derated accordingly. The NEC provides tables and guidelines for adjusting ampacity based on ambient temperature. It is important to note that the NEC is a minimum standard, and local codes or regulations may have additional requirements. Always check with the local authority having jurisdiction, or OJ, to ensure that your installation complies with all applicable codes. In addition to the NEC, other industry standards and best practices can provide guidance on ampacity derating. For example, the Insulated Cable Engineers Association, or ICEA, publishes standards for cable ampacity that are widely used in the electrical industry. When designing an electrical system, it's always a good idea to consult with a qualified electrical engineer to ensure that the system is properly designed and installed. An electrical engineer can perform calculations to determine the appropriate wire size and ampacity derating factors for your specific application. Ultimately, the goal of ampacity derating is to ensure that the conductors in an electrical system operate within their safe temperature limits. By following the guidelines in the NEC and considering all relevant factors, electrical professionals can design and install systems that are safe, reliable, and efficient. The NEC Article 310.15 provides detailed information on ampacity derating factors for various conditions. It includes tables for adjusting ampacity based on the number of conductors, ambient temperature, and other factors. The tables in NEC Article 310.15 are based on extensive testing and research. They represent the consensus of experts in the electrical industry on the appropriate ampacity derating factors for different conditions. When using the tables in NEC Article 310.15, it's important to understand the definitions and terminology used. For example, the term ampacity refers to the maximum current carrying capacity of a conductor under specified conditions. The term ambient temperature refers to the temperature of the air or other medium surrounding the conductor. The term continuous load refers to a load that operates for 3 hours or more at a time. The NEC also provides guidance on the selection of overcurrent protection devices, such as circuit breakers and fuses. Overcurrent protection devices are designed to protect conductors from overheating due to excessive current. The size of the overcurrent protection device must be matched to the ampacity of the conductor it is protecting. In addition to overcurrent protection, it's also important to provide adequate grounding for electrical systems. Grounding helps to protect people from electric shock and to prevent damage to equipment. The NEC provides detailed requirements for grounding electrical systems. When working with electrical systems, it's essential to follow all safety precautions. Always to energize circuits before working on them, and use appropriate personal protective equipment, or PPE, such as gloves and safety glasses. Electrical work can be dangerous, and it's important to be properly trained and qualified before attempting any electrical work. If you are not comfortable working with electricity, it's best to hire a qualified electrician to do the work for you. Remember to double-check all connections and ensure that they are tight and secure. Loose connections can cause overheating and arcing, which can lead to fires. Use the correct tools for the job, and make sure that your tools are in good working condition. Damaged or worn-out tools can be dangerous. Keep your work area clean and organized. A cluttered work area can increase the risk of accidents. Dispose of waste materials properly. Some electrical materials, such as fluorescent lamps, contain hazardous substances that must be disposed of according to local regulations. By following these safety precautions, you can minimize the risk of accidents and injuries when working with electrical systems. Always prioritize safety when working with electricity. It is worth noting that the NEC is updated every 3 years, so it is important to stay up to date on the latest changes. The NEC is a complex document, and it can be difficult to understand all of the requirements. If you have any questions about the NEC, it's best to consult with a qualified electrical professional. There are many resources available to help you learn more about the NEC. The National Fire Protection Association, or NFPA, offers training courses and publications on the NEC. The International Association of Electrical Inspectors, or IE, also provides resources for electrical inspectors and contractors. Online forums and websites can also be a valuable source of information. However, it's important to verify the accuracy of any information you find online. When in doubt, always consult with a qualified electrical professional. Ampacity derating is an important consideration for any electrical installation. By following the guidelines in the NEC and considering all relevant factors, you can ensure that your electrical system is safe, reliable, and efficient. The principles discussed here extend beyond simple residential wiring and are critical in industrial and commercial applications. In high-density installations, such as data centers or manufacturing plants, the number of conductors in a raceway can be very high, requiring careful consideration of ampacity derating. In these situations, it may be necessary to use larger conductors or to install multiple raceways to reduce the number of conductors in each raceway. In addition to the NEC, other standards and guidelines may apply to industrial and commercial installations. For example, the National Electrical Manufacturers Association, or NEMA, publishes standards for electrical enclosures and equipment. The Institute of Electrical and Electronics Engineers, or IEE, publishes standards for electrical power systems. When designing an electrical system for an industrial or commercial application, it's important to consider all applicable standards and guidelines. It is also important to consider the specific requirements of the application. For example, a data center may have stringent requirements for power quality and reliability. A manufacturing plant may have special requirements for motor control and automation. By understanding the specific requirements of the application, you can design an electrical system that meets those needs. Electrical systems are constantly evolving, with new technologies and innovations being introduced all the time. For example, solid-state lighting, or SSL, is becoming increasingly popular due to its energy efficiency and long lifespan. However, SSL systems can also introduce new challenges for electrical design, such as harmonic distortion and power factor correction. It's important to stay up to date on the latest technologies and innovations in the electrical industry. By doing so, you can design electrical systems that are efficient, reliable, and safe. Continuous load calculations are pivotal in many electrical engineering designs. Firstly, a continuous load, as defined by the NEC, is a load where the maximum current is expected to continue for 3 hours or more. Secondly, this distinction is critical as the NEC mandates specific rules for circuit sizing and overcurrent protection to account for the prolonged heat generation that continuous loads induce. Thirdly, the standard requirement is that the overcurrent protection device, like a circuit breaker, is rated not less than 125% of the continuous load. Fourthly, this requirement stems from the need to prevent nuisance tripping and ensure the breaker operates reliably without being unduly stressed by the prolonged current draw. Fifthly, to illustrate this, if a continuous load is expected to draw 20 amps, the circuit breaker should have a minimum rating of 25 amps, as 20 amps multiplied by 1.25 equals 25 amps. Sixthly, conductor sizing is intrinsically linked to continuous load calculations. The conductors must be sized to handle at least 125% of the continuous load, ensuring they do not overheat and cause a fire hazard. Seventhly, this sizing requirement is detailed in NEC section 210.19a for branch circuits and 215.2a for feeders. Eighthly, therefore, for the same 20 amp continuous load, the conductors selected must be capable of safely carrying at least 25 amps continuously. Ninthly, the conductor's ampacity, as listed in NEC tables such as 310.16, must be equal to or greater than the calculated load. Tenthly, failing to correctly account for continuous loads can lead to various problems. Overheated conductors can degrade insulation, which in turn can lead to short circuits, ground faults, and ultimately electrical fires. Additionally, undersized circuits can cause voltage drops, resulting in equipment malfunction or reduced performance. 11thly, in scenarios where multiple continuous loads are supplied by a single feeder, the cumulative effect must be considered. The feeder conductors must be sized to handle the combined continuous loads plus any non-continuous loads, again with the continuous loads increased by 125%. 12thly, this calculation can become complex in large commercial or industrial settings, necessitating careful load analysis and circuit planning. 13thly, moreover, the type of load significantly influences the continuous load calculation. Lighting, HVAC systems, and continuously operating machinery are common examples of continuous loads. 14thly, in contrast, intermittent loads like appliances or infrequently used equipment are generally considered non-continuous. 15thly, in addition, the presence of harmonics can further complicate continuous load considerations. Nonlinear loads, such as electronic devices with switching power supplies, generate harmonic currents that can increase the heating in conductors and transformers. 16thly, in such cases, the neutral conductor, in particular, may carry significantly higher currents than anticipated, requiring an oversized neutral or other mitigation strategies. 17thly, continuous load calculations also extend to equipment ratings. Transformers, for example, must be sized to handle the total continuous load plus any non-continuous loads, with appropriate derating factors applied based on ambient temperature and other environmental conditions. 18thly, the nameplate rating of the equipment should always be carefully reviewed to ensure it is adequate for the intended application. 19thly, moreover, energy efficiency considerations also tie into continuous load calculations. Optimizing circuit designs to minimize losses not only reduces energy consumption but also lowers the heat generated within the electrical system, improving overall reliability and safety. 20thly, in addition, regular maintenance and inspection of electrical systems are essential to identify and address any issues related to continuous loads. Over time, connections can loosen, insulation can degrade, and equipment can age, all of which can affect the performance of the circuit and potentially create hazards. 21st, the NEC is very specific in its requirements for continuous loads, and careful adherence to these rules is crucial for ensuring safer and reliable electrical installations. Understanding the underlying principles and proper application of these calculations is fundamental knowledge for any electrical engineer or electrician. 22nd, there are numerous software tools available to assist in continuous load calculations. These tools can automate the process and help to identify potential issues, but it's important to verify the results and understand the underlying assumptions. 23rd, these software tools are often integrated into larger electrical design packages, providing a comprehensive solution for system planning and analysis. 24th, in addition, ongoing training and education are essential to stay current with the latest codes and best practices. The electrical industry is constantly evolving, and it's important to keep abreast of new developments. 25th, many organizations offer courses and certifications related to continuous load calculations and electrical design. 26. By investing in ongoing professional development, electrical professionals can enhance their skills and knowledge, ensuring they can safely and effectively design and maintain electrical systems. 27th. It's also important to maintain accurate records of all electrical work, including load calculations, circuit diagrams, and equipment specifications. These records can be invaluable for troubleshooting and future modifications to the system. 28th, proper documentation is often a requirement of local electrical codes and can help to ensure compliance with safety regulations. 29th, continuous load calculations are not merely a box-ticking exercise, but a fundamental aspect of electrical safety and reliability. By carefully considering all relevant factors and applying sound engineering principles, it is possible to design and install electrical systems that operate safely and efficiently for years to come. 30th, in addition to the above, the inspector holds the ultimate authority to question and potentially reject designs that do not fully comply with code. 31st, because of this, always adhere strictly to the NEC, continuous load requirements and the correct calculation methods for conductor ampacity, overcurrent protection, and equipment sizing.